Okay, like I said, this is for not only Monday but Friday. So this was a little bit long, and I'll when I send the email when I post this and send the email, it'll be like, oh, okay, that makes sense. All right. So anyway, all right. So here's a parallel plate capacitor, and we'll deal with these a lot in this course because they just kind of and basically what a capacitor does is store charge. It acts like a battery. We'll learn a lot more about that later on. But we've got this thing called charge density. So they just take a little portion of this electric field here, but there's going to be electric field oozing out of here. It's going to be a solid block of electric field. Just imagine this as an Oreo cookie, all right? And these are the two plates, an Oreo cookie, and the frosting on the inside is the electric field, all right? So they're just taking a little piece of it. Now, you probably noticed that the equation of the electric field is over R squared. So that means it gets really weak really fast. What do I mean by that? Well, look here. Here's what we mean. We've got this. We got the E field. So here's the equation of the electric field, which is equal to KQ over R squared. So as R gets big, E goes to 0. All right, the electric field dissipates, and it gets big fast, so it dissipates pretty quickly. Now, inside the parallel plate capacitor, though, the E field stays the same the entire time because they're really, really close together. All right, for the most part, they're really we let the E field for our purposes, the E field will always stay the same between the two of them. So since we got the frosting, how do we compute the E field of the frosting inside that Oreo cookie? All right, and this is how we do it. We take E is equal to the total charge on one of the plates. Pick a plate, doesn't matter because it's the same on both. So you either compute the E field coming from here or the E field coming to this one. So let's just take the positive plate, the total charge on that plate, all right, divided by this little E naught, this permittivity of free space again, times the area of the plate. That's how you do it. That's all there is to it. Okay. So for that parallel plate capacitor, this is going to be kind of long. Is equal to Q, charge coming out, K times the area. All right. Let's talk some more. Oh, not K, E. Little echo not. E. All right. Okay. So electric field lines. Lines of force provide electric field lines are lines of force. In other words, if I put a particle in here, it's going to feel a force. If it's a positive particle, positive charge is going to feel a force pushing this way. If it's a negative charge, it's going to hop on the bandwagon and want to come this way. All right. Electric field lines are directed away from positive charges and toward negative charges. Electric field lines always begin on a positive charge and end on a negative charge and do not stop in mid-space. So in all of a sudden, here's a parallel plate capacitor. We don't deal with the fringes out here. People deal with the fringes out here, they're called physics majors and they're in physics 460. That's when you deal with the fringes. All right. We don't care about that. But if you're building solid state stuff, you do worry about that, right? So they don't go to 0 in the middle anywhere. All right. And then the number of field lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. Okay. It's proportional to the magnitude of the charge. So both of these have this is a positive Q and a negative Q. So they got the same number. So what does that mean? What does that mean? I'll show you real quick. Here's what that means. So if I have, let's say I've got a positive 4Q here, and I've got a negative 2Q here, and a negative 1Q here, and a negative 1Q here, then it'll look like this. It'll look like that. Notice there's 4 coming out of here, 1 going into this one, 2 going into that one. All right. So that's the way it works. Now, if I brought all of these together and brought all these charges together, what would happen? The electric field coming out of here would equal 0 because they're all, so if I draw a circle around this, the electric field coming out of there is 0. That's kind of cool. All right. Electric field lines don't cross. This thing has always kind of bothered me. There are 3 things wrong with part A of the drawing. What are they? Oh, I see. The electric field line's coming out of here. Oh, I got a guitar lesson in 30 minutes. Now you know my personal business. All right, I got 1, 2, 3, 4, 5 electric field lines coming out of there. 1 going there, 2 going there. So that's wrong there. They're crossing here. They're in proportion to each other. Notice the negative charges are getting the thing. So this seems that's, and then they cross here, and you can't do that. Okay. And they're out of proportion here. Out of proportion. The proportionality is correct here. This proportionality is not right. There should only be 1 coming here, 4 going there. Or, yeah, 4 going there, 2 and 2. That's why I should have drawn mine too. Okay? Okay, now, static equilibrium. Here we go. We're going to talk about some stuff here that's kind of heavy-duty theory, but this slide, conceptual questions. All right, at equilibrium under electrostatic conditions, any excess charges resides on the surface. So if I put a bunch of little bitty electrons here in the middle of this solid sphere, guess what happens? They all come out here and spread themselves out in equilibrium on the outside. The conductor shields any charge within it from electric fields created outside the conductor. In other words, this is why like black boxes on airplanes have a metal out casing. Your computer has metal casings because it keeps because any electric field is going to be attracted to this negative charge and nothing gets inside here to the workings of what's going on inside there. Okay. The electric field just outside the surface is perpendicular to the conductor under electrodes. So electric field lines are perpendicular when they come out. Okay, notice that obviously they're perpendicular here, but they're also perpendicular when they come in. The electric field inside is 0. A charge is suspended. Okay, so this is just theoretically. Let's see if we can hang a charge on the inside here. A charge is suspended at the center of a hollow electric neutral spherical conductor. Notice it's neutral because they'll show that this charge induces a negative Q at the interior surface. So this positive charge draws a line, the negative charges attaches them right there. And then a charge of Q on the exterior surface of the conductor, which is equal, all of these charges added up equal this charge, and that's the electric field coming out of it. So what's the magnitude of the charge? It's a charge density type thing, and here it is. So all of the charge coming out of there is equal to KQ over R squared, the distance away. However, it's a charge density thing because this is a sphere. Here's the surface area of the sphere. Just like with the parallel plate capacitor where they used, so they're going to use 4 pi echo naught R squared because 4 pi R squared is the surface area of a sphere divided by Q. That's the surface area. So the surface area of the sphere. So E times A, that's called the electric flux. Yeah. This is all, so Gauss's law says, basically here's what Gauss's law says, that the electric flux, I can sum up all of these charges and get the big massive Q over E naught, and that'll give me my electric flux. It becomes a very complicated integral problem, three integral problem. We don't mess with it. Physics 250, they kind of mess with it, but that's why we make everything a sphere. So Gauss's law, we make everything a sphere. Okay, nothing on the inside. The electric field on the outside of a sphere is equal to Q over 4 pi r squared, because this is the surface area of the sphere, times echo naught. Piece of cake, because we get it from here. Here's the surface area of the sphere. Here's Gauss's law. Here's the big Q of all of these charges on the surface, okay, this thing. We shrink it just down to a point. That's all we do, okay? And so Gaussian surface, we can either use something that's convenient to use is a cylinder, a square, or a sphere. And since three-dimensional, it's easiest to work in spheres. That's why we like to use spheres. There you go. We are done. We're not going to go into this option copiers and computer printers, paths of scanning laser beams. We're not going to do any of that stuff. We're done. So that's chapter 18. So this will cover Thursday and Friday, or Friday and Monday's lecture out here. Because I got to go to a guitar lesson in 25 minutes. Oh, let me turn this off.